of sustainable sales and marketing efforts in Heidelberg Material Concrete business in Canada and in the Pacific Northwest in the United States. This includes working with architects, engineers, and designers towards lower carbon sustainable solutions in the built environment. He has over 20 years of experience in a variety of civil engineering sectors, including the technical promotion of cement and concrete products, structural design of underground infrastructure, waste diversion planning, and stormwater management. His previous experience includes roles with the Cement Association of Canada and Lafarge Canada, Inc. His presentation will be Accelerating to Zero. Please welcome Shane.
Thank you very much. So I'm going to give a little bit of insight into what we're working on at Heidelberg Materials in terms of carbon capture utilization and storage. A little bit of context first. We're a vertically integrated construction materials company specializing in cement, aggregates, and concrete. We also have some asphalt and concrete pipe operations as well throughout North America. We undertook a rebranding exercise in 2023, so you might know us better by some of our legacy brands like Ocean, Rempel, Inland, Hanson, Lehigh Hanson, and the like. And like a lot of companies out there, we have published a series of sustainability commitments. And we've grouped those sustainability commitments into a number of different key categories. Having a safe and inclusive workspace, being nature positive with actions around biodiversity and returning some of our aggregate quarries to community assets in the future, looking at circular economy and resiliency principles, recycling concrete aggregate, looking at use of waste materials from the slag industry, or from steel industry, I should say, for slag, coal industry for fly ash, etc. And then the big one for us is net zero and actions to reduce our carbon footprint. And because of our net zero commitments, we've published what we call our concrete promises, some of which are highlighted here on the screen, which were revealed about a year and a half ago at our Capital Markets Day. And some of the key ones that I generally highlight is that 50% of our revenue will be sustainable revenue by 2030. And sustainable revenue for us means meeting certain criteria in terms of how low carbon it is, how much recycled concrete material is being incorporated. And then the other one is that top number, which is we commit to reducing our carbon intensity of cement to 200 or to 400 kilograms of CO2 per ton. So many of you are probably familiar with the old rule of thumb that 1 ton of cement equals 1 ton of carbon. We're trying to get down to 400. And for some context, the lowest EPD that we have for a straight cement product in North America is at our Delta, British Columbia cement facility, where we're at 679 kilograms of CO2 per ton. So quite a ways to go to get to that 400. You know, that is a global number, so some countries are going to be pulling a little bit heavier than others, but nevertheless, we have a ways to go to get there. And Rob Cooney is going to be going over a little bit of what the industry's action plan is to get to the goal of net zero concrete. And we're aligned with that as a member of the Cement Association of Canada. But we also have our own roadmap that's very similar in terms of what we're looking at, but we group it slightly differently in terms of where we're focusing our attention to help drive down to that goal of net zero. Those 4 buckets are innovative products and technologies, the circular economy, carbon capture utilization and storage, which is really I'm going to be focusing most of the talk on here today, and then the concept of natural carbonation. And many of these solutions are available today. On the innovative products and technology side of the equation, we have Portland limestone cements. We brand them as EcoCem in North America. We also have blended cement products. Our EcoCem Plus product is a PLC with 20% fly ash already blended in it, coming right from the cement plant. Those are contributing relatively significantly to reducing the emissions associated with the cement product. We're also utilizing alternative lower carbon fuels. So across Canada, cement facilities have started to implement alternative fuel programs where they're allowed to use construction demolition waste, wood waste, non-recyclable plastics, other waste streams, depending on the region and where they're at. And this has a pretty significant impact on the carbon intensity of cement as well. We have our British Columbia plant is already utilizing 20 to 30% substitution of these materials, and our goal is to get to 50% substitution across all of our plants in North America. And then the other one that's happening now is natural carbonation, and I think it was a subject on a number of the different talks going on here today at ACI. I'm not going to get into the nitty-gritty here because it can be controversial about what it exactly means, but there are efforts underway to better quantify in a conservative manner what the impact of natural carbonation is, and we'll start to see that reflected better on our LCAs and our EPDs at some point in the future. And that brings us to the final product, concrete. And today there are a lot of different levers that are available for low carbon concrete. And again, it's been covered pretty well here at ACI with the various sessions that are going on. But ultimately we have a number of different levers at our disposal as concrete producers to demonstrate carbon reductions. Whether it's looking at our aggregate gradations and getting better particle packing and strength out of the skeleton of our concrete mixes, looking at different admixture products to help with water reduction and strength enhancing properties. The big one, of course, is SCMs. Everyone's very familiar with the use of fly ash or slag to reduce the amount of cement that's going into the mixes. Cement types like Portland limestone cement. Days to strength maturity is a big lever for us, being able to extend a mix from 28 days to 56 days to 91 days. Those are tremendous levers for significantly reducing the carbon impact of concrete. And there are some new digital solutions as well, like maturity monitoring technology or in-truck monitors or probes that sit in the drum of the truck and create different feedback loops for how that concrete's performing, so that based on the given climate temperatures of the day or the actual mix that's going out the door, you can get that feedback loop and make incremental improvements to your concrete mix as you optimize towards carbon reductions. And right now, you can pretty comfortably deliver about 30 to 50% carbon reductions using an EPD when compared against the regional industry average benchmarks, if there are no limitations in place. If you just had a slab that you're going to pour that nobody's ever going to stand on, you could pour a very low carbon concrete slab. Unfortunately, when we get into construction, there are lots of limitations that get put in place, whether it's workability, pumpability, finishability, or schedule. You need higherly strength concretes to make your suspended slabs when you're doing high-rise construction, and that does not fall in line with our carbon reduction efforts. So there's a lot more to be done to be able to deliver the deep carbon reductions that we're all chasing as an industry. And we have to look to the future to be able to deliver those carbon reductions. And where Heidelberg Materials is concerned, where we're really making significant investments in trying to demonstrate a leadership position, is in the future with carbon capture, utilization, and storage technologies. So another one of our concrete promises that we've put out to the marketplace is that we hope to capture 10 megatons of carbon cumulatively by the year 2030. And we're going to do that by constructing a number of CCUS plants or CCS plants without the utilization component. There's a number that are highlighted on the screen. Many of them are located in Europe, in Germany, the UK, France. The first one that's going to go online later this year, within the next month or so, is in Brevik, Norway. So we're very excited about that in the near term. And then longer term, we have a couple of solutions or plants that we're targeting to have in North America as well. One in Edmonton, Alberta, which I'm going to focus on a little more deeply in subsequent slides, and then another one down the line in the 2030 time frame for Mitchell, Indiana. And that brings me to our Edmonton project that's been publicly announced, and we're working hard at getting it over the finish line to be able to break ground on construction. This project is going to capture 1 megaton of carbon annually as a result of once it's fully online. Ideally, it's going to be completed by 2029. There are two main barriers to being able to go forward with CCUS. One of them is cost. It takes a tremendous amount of cost to be able to build one of these facilities. What we quoted when this plant was first announced was $1.4 billion in 2023. And as we know, costs have only gone down since 2023, so we're going to be able to go forward with this hopefully soon. But kidding aside, there's a lot of uncertainty out there right now, but we do have funding secured with federal government, with the provincial government. It's something that we're hoping to make our final investment decision on in the near future, and then be able to break ground and deliver this solution to North America. One of the questions we get all the time is, why Edmonton? Why would you put a carbon capture plant in Edmonton? And from a market demand perspective, it doesn't make a lot of sense. We'd probably prefer to put it out on the west coast in the Pacific Northwest or in British Columbia, where there's a higher demand for green products. But the other limiting factor when it comes to CCS is that you need storage. Storage needs to be available in your local geology, and Edmonton and Alberta more broadly is ideally situated in that regard, as there are a number of what we call natural geologic storage hubs, many kilometers underground, that are able to accept the carbon that's going to be captured, not only from this project, but other projects throughout Alberta and Saskatchewan. And ultimately, this is probably pretty tiny for everybody, but I'll try to walk through using the color coding that's outlined on the screen. The impact of the carbon capture as it's going to be seen on an EPD for both cement and concrete. This is the tale of two products as divided down the middle by this dashed line. To the left of that dashed line is the cement story, and to the right is the concrete story. The blue bar are the emissions that are being generated today. The green bars are the emissions that are going to be reduced as a result of the levers that have been identified in the previous slides. And so for cement manufacturing, you have the coring of the raw product itself, which is not very carbon intensive, which then needs to be transported to the cement production facility. So in Edmonton's case, they are transporting about 200 kilometers away in the Jasper geography by rail to Edmonton. Then you have the electricity that's being consumed by the cement manufacturing process, which is relatively significant. And unfortunately in Alberta, we have a pretty carbon-intensive electricity grid that runs on natural gas. So that gets us to that point there. From there, you have the cement manufacturing process itself. And I imagine everyone in this room is pretty familiar with the emissions coming from process emissions, the calcination process, and then the combustion emissions that are required to get those kilns to 1500 degrees Celsius, primarily utilizing natural gas, coal, and in Eastern Canada you use things like petcoke. That ultimately gets us to where we're at now at about 789 kilograms of CO2 per ton of cement. As we move forward and introduce alternative low-carbon fuels, you're going to be displacing the fossil fuels that you're consuming. But then because we're capturing the carbon that's associated with biomass, whether it's wood waste or another biomass source, from a carbon accounting perspective, there's an added benefit that's being captured and illustrated by that bar there. Then you have the direct impact of carbon capture itself, capturing about 95% of the emissions that are being generated by that plant. And interestingly, for this project, we're also incorporating a combined heat and power plant as part of this project that is going to get us off of the grid and generate our own electricity right on site. And we're going to be capturing the emissions that are associated with that process as well. And so that's being illustrated by this lighter green bar, ultimately getting us to a point that's going to vary somewhat depending on how efficient the operation is going to be, but the EPD is ultimately going to say somewhere as low as minus 56 kilograms of CO2 per ton of cement or 67 kilograms of CO2 per ton of cement. So either way, essentially a net zero cement product at our gate level at our plant in Edmonton. As we move on to the concrete side of the equation, you have the transportation of those raw materials, the cement and aggregates, to the concrete site. And what's being modeled here is a 1,000-kilometer rail journey from Edmonton to the Vancouver marketplace to demonstrate how far we can go with this. But rail is a relatively low carbon-intensive mode of transportation. Then the manufacturing process itself, that at the EPD level, at gate with our concrete, we'd be slightly above zero, probably in the 35 kilogram area. We'd see the transportation, module A4 of that concrete to the project site, and then any heating, hoarding, pumping, vibrating, etc., reflected in the construction stage, ultimately getting us to somewhere around 40 or so kilograms of CO2 per cubic meter, and then we rely on that process of natural carbonation to get us down close to zero or possibly even into the negative territory with that concrete. So the industry is trying to get to that target of net zero by 2050. We're hoping to demonstrate that by 2029, which I think as an industry we're very excited about, and as Heidelberg Materials we're quite excited about as well. A little more detail on what the actual process looks like. And so what's going to happen is we're still going to have the cement operation as it stands, pretty much as it is today, and build a separate CCUS facility just to the west of where the cement plant is located. We're going to put a literal cap on the stack of the cement manufacturing facility that's going to transport that flue gas into the carbon capture facility. It's going to be scrubbed the same way flue gas is scrubbed now to reduce a lot of the different emissions that are associated with that, cleaned a little bit more of its SO2, and then goes into a different area of the operation where it's exposed to what's called an amine solution. That amine solution is chemically formulated to absorb CO2 as it passes through while that amine is cool. Once that CO2-rich amine solution settles at the bottom of the tank, it's transported to another area of the operation where it's heated up, and as a result of that heating process, the CO2 is released as a very pure form of CO2, which we are then pressurizing into liquid form, putting into a pipeline, transporting 25 kilometers away, 3 kilometers underground into one of these natural geologic storage hubs. goes well below the freshwater aquifer down into a saline aquifer within this sponge-like rock formation where there's interconnected pore space for that CO2 to infiltrate. One of the questions that always comes up is how can we guarantee that it's permanently secured there? One of them is through measurement, monitoring, and verification, which the Alberta government and our partner Enbridge are going to handle in terms of verifying that the carbon's actually going down and staying down. The other thing to remember is that it's not a gas when it goes down there. It is a supercritical dense fluid, so it's not constantly trying to rise up and escape. It's going to sink and spread throughout that interconnected pore space. We're also going to get some what's called capillary trapping, which is just trapping some of that CO2 within the pore space of that sponge-like rock formation. And then over longer periods of time, we're going to have solubility trapping as that CO2 chemically interacts with the saline. And then over a much, much longer time frame, it's going to actually remineralize in place and revert back to limestone. So it is a very permanent and safe solution ultimately. And here's another view that just kind of demonstrates a little more visually what those layers of geology look like as you go 3 kilometers down, and then a little bit more detail on what the time scale is going to look like for when that permanency is being achieved towards that goal of mineral trapping long term. So when we come and look at low carbon concrete today, there are a number of challenges that we face. I kind of alluded earlier to schedule. Schedule is probably the biggest driver right now that limits our ability to demonstrate really deep carbon reductions using the traditional levers that we have today. That's something that is just can't be addressed using the solutions that are currently available. And as we've seen with things like Portland limestone cement and other novel SEMs that are being introduced into the marketplace, there's a lot of reticence in the design community, in the regulating community to accept these solutions as they come. It's been a 15, 16-year battle with Portland limestone cement, and the solutions are coming much faster than they can be evaluated. The benefit of this carbon capture solution is that it's a post-production process, doesn't alter the chemistry of the cement at all. It's exactly as it is today, and you're avoiding all these challenges that we're currently experiencing with low carbon concrete. So again, something that we're very excited about and hoping to introduce as early as 2029. And with that, I'm very happy to take any questions you may have.